Okay, we were unable to get into Zoom, unable to log into anything for a little while, but apparently uh, that's been resolved, at least for the moment. Now that I'm in Zoom, I think we're going to be okay with Zoom because I'm talking to Zoom, but we could get kicked out. In the meantime, we discussed, um, actually, I can get the slide of down to the lower corner. Okay, the first thing we did was I said, I got one domino here, the bottom at 300, 400 Celsius, the top at 300 Celsius or Kelvin. Yeah, it's it. We don't want 400 and 300 Celsius. We want 400, 300 Kelvin. 400 Celsius, we don't have the means to get anything but flames that hot in here. Okay. Um, Actually, if we tried, we could, but we're not going to. Okay. 400, 300. Question then, if at this thickness, we were conducting heat energy at the rate of 8 joules per second. Okay. Then at what rate would we be conducting heat energy if we had a stack of five of these, assuming these are of equal thickness? They are, but assuming they were. Okay. And that actually inspires me to another experiment. Okay. Not sure we're going to get to it, but we'll try. All right. So the question is now, if the bottom is at 400 and the top is at 300, at what rate would energy be flowing through here? Well, we digress to the question of, well, okay, what would the temperatures at this surface and then at each interface between the dominoes, what would the temperatures be? There's 400 here, there's 300 here, and then domino by domino, what would the temperatures be? And some people came up with equal temperature differences over the dominoes, and some people came up with unequal because of the various intuitive ideas. Okay. And it wasn't real specific. Right after this thing is at 400, the top still isn't going to be changing much because he has to flow gradually through this thing. You're not going to set up a steady state heat flow in this stack for at least tens of minutes. Okay. We've measured these before, and it takes a while for the heat to flow. Okay, so at the beginning, this bottom domino is going to be a lot hotter than the one above it, and it's the one above it is not going to be all that much hotter than the one above it. After it's been going a while, you're going to have a uniform heat flow. Now, I'm assuming that these are surrounded by insulation. Okay, so there's no heat loss, no significant heat loss out of the sides. So the temperature versus position, if this is T equals 400 on this line, this line is T equals 300, and you've got a little break in the y-axis because zero is down here. That would be absolute zero. There's no point in going down to zero. We can't even achieve absolute zero ever anywhere. And we're pretty well confined to temperatures in the range of 250 to 400 or something. Okay, so anyhow, at the beginning, if x is measured in domino thicknesses, we're going to have x equals 0 here, x equals 5 here, and we're going to have something that looks roughly like this. Now, there are differential equations that you can solve, and they're not that hard to solve that tell you exactly what you would expect given various constants and so forth. But conceptually, it's like this. Now, in earlier, it's more like this, but it's going to approach a straight line. Why is the temperature versus position going to approach a straight line? It's because the rate of heat flow is proportional to the temperature gradient. Okay? And people mention temperature gradient. People were familiar with the idea of temperature gradient. That is, if one of these dominoes has a greater temperature change than another one, then more heat is going to be flowing through it than through the one with the lower change of temperature, right? But if you have a steady state, and then again, disregard the fact some dominoes are a little thicker than others, but if you have a steady state, the temperature change across every domino has to be the same as across every other because the rate of heat flow is proportional to the temperature gradient. Fair enough? Okay, so we first get that idea. So let R be the rate of heat flow. We're just going to say it's proportional to the temperature gradient. Now, at steady state, delta T over delta X is the same as dt dx because the temperature gradient is constant throughout. Ponder that if you don't understand it. Next model, I've got these steel plates. I had a stack of these about this high, surrounded by styrofoam. Again, same model. I had to bring the stack up here, but you can't see inside it, so it doesn't really matter. Just imagine this surrounded by some insulation, except on top. Assume the top stays at 300. It's in a room that's at about 200 and down the 290s. Okay. But the temperature of the top has to be such that it's giving up heat to the room. So the top's going to be a little warmer than the air in the room. Now, I don't know exactly how that's going to work out. That depends a lot on convection and air circulation and other things we don't have a lot of control over. Okay. So we've got this stack. And again, assume the bottom of the stack is at 0. The top of the stack is at, I said 0. Bottom of the stack at 400, top of the stack at 300. Okay, so that's what I've indicated here. This stack approaches just a continuous bar. It's got a couple of holes through it and stuff. So there's some anomalies involved, but we're going to treat this as a continuous bar with a constant temperature gradient. And we're going to assume that the block looks like this: temperature below, temperature above, and insulation around, and I'm not going to attempt to draw the insulation. Well, I asked them, I set the stack down for people. I asked them, okay, estimate the temperature gradient. Quite sure what to do, but somebody said, delta T over delta X or dt dx. Okay, so yeah, how are you going to use that to estimate? Well, you got to know what the distance is between here and here. Then you divide the temperature difference by that distance. So it's going to be negative 100 degrees divided by whatever number of centimeters. Ask people how many centimeters. Nobody wanted to estimate. Okay, nobody said 5 miles, so that's good. But nobody wanted to do an estimate. Well, you look at it. If you think it's 10 centimeters and it's 5 centimeters, you're still reasoning out the problem, it doesn't matter. Now, if you say 3 meters, I know that you're not making a serious estimate, but I say, go ahead and use it. Okay, you figure it out for a 3 meter stack. We can't even put that inside the room, but you can figure it out. What do you do with the quantities? Your temperature gradient is going to be negative 100 degrees Kelvin, negative 100 kelvins is the way we usually say it, divided by the number of centimeters. Well, it turns out people wanted to estimate 5 centimeters, which is about what I was thinking. Then I measured it, it was 4 centimeters. So you can use 5 or 4, doesn't matter. Okay, so the temperature gradient okay, well, delta X is your distance and the direction of heat flow. In this case, it looks like it's going to be, okay, well, I measured the stack and then I put one of these next to the stack this way and one this way. And so that looks like about 6 by 4. Then I measured it and it was. That's no big coincidence because these things are in centimeters. So I had a pretty good chance of getting it right, at least a 30% chance. And I lucked out a little bit. Okay, delta T over delta X would therefore be negative 100 Kelvin over, okay, the 4 centimeter distance here. Then I asked, what's heat flow per square centimeter of cross-sectional area? Okay, and people wanted to do all kinds of things with that. Okay, somebody wanted to have something in cubic centimeters. Okay, now that's not an unreasonable thing because if you want to know how much heat is contained in this thing, if you know the specific heat and the temperature, you're going to need the volume. Okay, so it's not a bad thing to think about volume, but if you think about cross-section is not measured in units of volume. Cross-sectional area is an area and it's in square centimeters. So how much heat flow per square centimeter of cross-sectional area? And the answer to that came out, well, if it's cross sections, a 4 centimeter by 6 centimeter rectangle, then area cross section equals 24 square centimeters. If the rate of heat flow is watts, which might be fairly reasonable. I think it might be a little bit lower than that for the block that we looked at. Okay, 4 centimeters this way, 4 centimeters this way, 6 centimeters this way. But if the rate of heat flow is 8 watts, and the rate over cross-sectional area is 8 watts over 24 square centimeters equals about 0.33 watts per square centimeter. Now, if we hadn't measured it, if you were just estimating 4 by 6, you'd probably just say 0.3. Okay. Using slightly different numbers. Some people came up with 0.25. They're using different numbers. 20 square centimeters. Okay, that would be 0.4 or something else. But people got reasonable results there. Okay. Now, somebody was familiar with the formulas and so forth and said, this has to do something with K. And it does, but you're not going to reason out these answers using K. You can use this information to determine K if you know how things are related. Okay, well, how are things related? What affects the rate of heat flow? Rate of heat flow is proportional to delta T over delta X, or dt dx if you wish. And you need dt dx if you don't have a uniform bar. So your rate is proportional to delta T over delta X. And I might be using bad symbols here. And sometimes R stands for rate over cross-sectional area. Well, this means then that rate is proportional to the cross-sectional area times temperature gradient. I'll use dt dx because that's general. If it's constant, we can just use delta T over delta X. And in this case, it's constant, okay? So the rate is proportional to cross-sectional area times delta T over delta X, or dt dx. So rate equals a proportionality constant. Does anything else govern the rate? Is the rate determined by anything but the cross-sectional area and the distance along the path that the heat flows? Well, look at the introductory problem sets and see what you think, okay? If that's the case, then in this example, K equals what? It's the rate at which energy is transferred divided by the cross-sectional area times, I'm going to use delta T and delta X so I don't have to get fancy. For this situation, delta T over delta X is fine. So we could write it like this. We just write R delta X over ACS delta T. So what do you get for K? In this case, it's 8 watts over 24 square centimeters, which we already calculated here is 0.33 watts per square centimeter, times 4 centimeters over 100 K. Now, I got one thing wrong here. The rate of heat flow is the negative of this because heat flows in the direction of decreasing temperature. That makes sense? If not, read about it. It's explained. Okay. heat flows opposite to your temperature gradient. Your temperature gradient is positive. That means that's the direction in which temperature is increasing most quickly. And that's not the direction in which heat flows. It flows from hot to cold. So keeping the negative signs in here, I have a negative sign in front of the left side, but I have a negative 100K here for the delta T over delta X, which is consistent with what I wrote up here. Well, what's that equal? Well, the numbers come out real nicely. 4 goes into 24 6 times. So you have 600 on the bottom, you have 8 on the top, and you're going to get 0.0013 if I did it right. Let's add me a 0.08 and you divide that by 6. Yeah. 0.0013. Now it's in units of watts times centimeters. Over centimeters squared Kelvin. And of course, this centimeter divides that centimeter, so you get watts per centimeter Kelvin. Or joules per centimeter second Kelvin. Okay, change your watts, joules per second. So you can express this unit. You wouldn't express it this way because you have the centimeter squared here and the centimeter here. So there it is. Now, was my 8 joules per second reasonably accurate? I think it was in the general ballpark, within a factor of 2 or 3 maybe. But why don't we just check it? Why don't we just look up thermal conductivity of steel? Okay, do you want to do it or you want me to do it? Well, I got a keyboard here, so it's going to be quicker for me. I don't remember what the thermal conductivity of steel is because I don't do that much with conductivity except once a year. And now that I'm getting older, I don't remember what I did a year ago. Okay. Okay, well, I got to be a little bit humble. No, actually, wait a minute. This is 60. Never mind. This isn't too bad. Okay, it's 60 watts per meter Kelvin. And I was saying that that really goes against my intuition. You know, stack these things 4 centimeters high, held at 400 down here, and going up to 300 here. My intuition would be that'd be in the ballpark of 10 watts per square centimeter. Heat flow. Okay, heat current. Okay. And I'm going to use the word heat current because your model for what happens in an electrical conductor, and we're going to move into electricity pretty soon, is very similar to what's going on here. And we'll make that connection in a minute. Okay, so we got 60 watts per meter Kelvin. Now, if this is per centimeter Kelvin, then you got 1/100th of that, which would be 0.6 watts per centimeter Kelvin. This is the number of watts you would flow that would flow through 1 meter square. Well, he had a 1 meter square and it was 1 meter thick. Okay. In any case, when you go from meters to centimeters, your denominator becomes 100th is great, which means I didn't put my slash in there. Yeah, you figure it out. Okay. it comes down to the fact that you got a 100 centimeters in a meter and 10,000 square centimeters in a square meter, and 100 divided by 10,000 is 1/100th. Okay, so your conversion there would be 1/100th. So you get 60 would become 0.6. 0.0013. I still don't think I was that far off. So I got to think about that a little bit. You think about it. Now, the analogy I want to make with electrical conduction is that you want to think of electrical conduction in terms of the amount of current flow per unit of cross-sectional area. Okay? Just like here, we're thinking of the amount of heat flow per unit of cross-sectional area. Okay? So the thermal current is energy per unit of cross-sectional area. Um, it's energy per unit of time, which is power. You don't normally think of this as power. I'm gonna rewrite this. Didn't have enough room to write everything out. It's energy per unit of time over per unit of cross-sectional area. Choosing my words as much to fit them into available space as much as for clarity. Okay? You want to ponder that. You want to understand that in terms of what we just saw. Electrical current electrical current density is current per unit of cross-sectional area. A little more precisely, I don't have room to write it out, but just to get the idea in your head. It's current, well, it's per unit of cross-sectional area perpendicular to the direction of energy flow. Okay? So I could here say it's perpendicular to the direction of flow. And down here, perpendicular to the direction of flow. Here, we're going to call this J. Now up here, it's energy per unit of time. Why don't we say current per unit of time? Well, because really it's charge per unit of time. That's what current is. That makes sense? I'm running out of room. Myself a little room by taking this value that I got from the table, which has to be wrong because it's nowhere close to what I got. So whoever this engineering group was that made up this table, they must have been hallucinating something. They must have been using AI. I'm sure the table's accurate. Okay, that might be a little hard to read. So I'll note that current is charge per unit of time, so that this J thing, having current per unit of cross-sectional area, is just charge per unit of time per unit of cross-sectional area. Whereas up here we had energy per unit of time per unit of cross-sectional area. So that two expressions have an identical form. And they're also vector quantities. Because the energy flow has a direction. In the case of this thing, the direction is parallel to the axis of the bar or prism or whatever it happens to be, okay? And in the case of an electrical current in a wire conductor, well, the current's in the direction of the wire for reasons that we'll see in much more detail when we really get into the electricity. Okay? So if we were to take a battery, two leads off the battery, put one lead here and one lead here, make sure these things are nice and tight together. Okay? So we have a continuous conductor, energy would flow. The bottom would be at one voltage, the top at another. There'd be a voltage difference. Okay? So voltage is your field gradient. Now, I'm not going to explain what I mean by that until we do it in detail, which we'll probably start doing next week. Okay? So we'll just say voltage is analogous to temperature gradient. And if you have the same voltage over a shorter stack, you get a bigger gradient, okay? And actually, I think I said something that probably wasn't right. But anyhow, your gradient is voltage over length, voltage over the distance, okay? So it's actually voltage gradient. So that analogy to temperature gradient is a voltage gradient. which would be like delta V over delta X. Which is electric field. I started to say that very incorrectly. Too close to lunchtime. Okay. Here you got temperature gradient. Here you got voltage gradient. You got a pretty complete analogy. Now there's one difference in that heat can accumulate and your thermal gradient can be non-constant for reasons that your voltage gradient might not be. So there's not a perfect analogy, but it's a close analogy in the form of the equations, in the form of the formulas, in the form of the concepts. It's very, very similar. So you want to think a lot about this situation, which we'll do some measuring on in lab, if I can find everything I need. People walking around the hall. One more thing we observed. I've got I'm finding it difficult to hold these things so you can see them. I've got a couple of airsoft BBs in my hand here, and they're super glued together. Now, I don't know how well super glue is going to work with these BBs. I tried it with a couple of ping pong balls and it was worthless, worth nothing. Now, these BBs have a pretty high coefficient of restitution. If I drop the BB on a tile, I drop it from here. I don't know how well you're going to be able to see this, but it bounces almost as high as it was when I dropped it. I was watching the camera, so I wasn't able to catch the BB, but I might not have been able to catch it anyway. I don't know how level this thing is, but now I'm going to drop this pair of BBs on the surface. Maybe you can see what happens. Okay, it goes bouncing all over the place. And that time it bounced to a height that was kind of comparable to the initial height. So let's try it again. You can do just about anything and you can go off in just about any direction. Okay, caught that one. What happens is these BBs hit and some of the energy that they gain in falling is converted to rotational energy. So they don't bounce as high as a single BB, unless they happen to hit just perfectly and don't get any rotation. Meaning that some of the energy, potential energy that's lost here, goes into rotation. Okay. Now there's also energy lost every time you have a collision, every time it bounces. But it maintains quite a bit of energy for quite a while. Now, if I have two tiles and drop a BB and then bring the tiles together quickly, the tiles hit the rebounding BB, and every time they do, they add a little bit of velocity to them. So that if the tiles get pretty close together, that BB is going to bounce back and forth between the tiles very quickly, creating a pressure. If I had diatomic BBs, pairs of BBs attached together one way or another, a lot of that energy would go into rotation and you wouldn't get as much average force on the upper plate or the lower plate as far as that goes. think of that in relation to the kinetic theory and everything we've talked about with thermodynamics.